Well, you may recall that we have done stoichiometry on moles to moles conversions of substances. We've done stoichiometry in a chemical reaction from grams to grams. We've also used solution stoichiometry, where we've used the volume and the molarity of one substance to convert maybe to some volume of another substance. Well, we can do the same thing with gases using their pressure, volume, and temperature. And so we're going to add to our general stoichiometry scheme. So just as a reminder, the mole-to-mole conversion, moles of A converting to moles of B, this conversion is the only way we can convert between two substances mathematically. We can't convert between substances using grams or milliliters or volume or anything else like that. We always have to go through this conversion step if we're going to mathematically convert between the amount of one substance A and the amount of another substance B. And for that reason, because we always have to go through this step in a stoichiometry, I call this the heart of a stoichiometry problem, because we're always going to go through that step. Now, you may recall that if we are given grams of A, that we can use the molar mass to convert from grams to moles, and then convert from moles of A to moles of B. And where do we get that conversion? We get that from the coefficients in the balanced chemical reaction. And once I have moles of B, I can then convert it out to grams of B using the molar mass of B, right? And we've done that sort of stoichiometry many weeks ago. Additionally, if we have some volume of a solution of A, I could use the molarity of A to convert from the volume of a solution to the number of moles. Remember, molarity is moles per liter, so I was able to use the molarity as a conversion factor. And of course, then I could convert out from moles of B to volume of solution containing B by using the molarity of the solution B. So that's what we've done so far. We're familiar with that, so we can do these sorts of stoichiometry problems. And we're going to add one now. Now, if I have the pressure or the volume or the temperature of a gas A, I can use the ideal gas law, PV equals nRT, to then convert from, notice there it is right there, moles of A. So if I have those values, PV and T of the gas A, I can plug them into my ideal gas law. R is a gas constant, I know that value, and I can solve for the number of moles. So I can get into this conversion. Similarly, wherever I have gotten my number of moles from wherever I started, once I convert to moles of B, I can also convert back out to the pressure, volume, and temperature. These are commas, pressure, volume, and temperature of gas B by using the ideal gas law, PV equals nRT, at the end of my stoichiometry. So there are a couple of different ways that I can approach this. Maybe I have a gas A, and I only have my pressure, volume, and temperature. So I would use my ideal gas law first to determine the number of moles of that gas. And then I would set up a stoichiometry dimensional analysis to convert the moles of A to moles of B. So I prefer to think of this as two separate math problems. Yes, you can set it up all as one long stoichiometry problem, but I think when we're dealing with gases, it's probably easier to keep it in mind as doing it as separate math problems. And I'm going to give you an example right down here. So we're going to work through this sample problem together. Okay. So it says how many liters, so we're looking for a volume, liters, of H2 gas would be expected to be generated. Aha, so the H2 gas must be a product that is going to be generated by the reaction of, I'm running a chemical reaction here, okay, of 30.0 grams of aluminum metal and an excess of hydrochloric acid. So I'm running a reaction between aluminum and hydrochloric acid, and I'm going to be generating as one of my products H2 gas. It's giving me amounts of my two reagents. An amount of the aluminum is 30.0 grams, and an amount of the hydrochloric acid, which is an excess. Fortunately, since one of my reagents is in excess, I don't have to do more than one stoichiometry problem, so this is not a limiting reactant problem. I'll just do one stoichiometry starting from the aluminum metal to go to the hydrogen. And then they tell us what the pressure is at 0.950 atmospheres of pressure and the temperature, 23.5 degrees Celsius. So let me just identify some of the things that they're giving me. They're giving me volume, or they're asking for volume, and they're giving me grams of aluminum. They're giving me pressure of the gas, and they're giving me temperature in Celsius, which I know that since it's a gas, it will have to be converted to kelvins. So let's see if I can strategize how I'm going to approach this problem. I'm asked for a volume of H2 as my goal for this problem. So let's look at our scheme. If I'm being asked to solve for a volume of a gas, am I going to use this approach to get the volume of a solution? No, because this H2 gas is not a solution. So I'm not going to use this approach that uses molarities. Am I going to use that old conversion factor that you may have learned, that 22.4 liters per mole? No, because this is not being done at STP. So I'm not going to use that one either. Instead, once I get the moles of H2 gas from my stoichiometry, I'm going to use this approach. I'm going to take my answer for moles of H2, and then I'm going to plug it into this equation as a separate calculation. And since they've given me my atmospheres and my temperature, which I will need to convert to kelvins, I can plug all that in there and solve for the volume of the gas. Well, okay, that's great. Once I have the moles of H2, I can plug it into this equation and solve for the volume of the gas. How do I get the moles of H2? Well, you notice that that has to be a stoichiometry problem. So I'm going to have to do a stoichiometry problem that gives me the moles of H2. And then once I have that answer, I'm done with the stoichiometry. And then I'm going to do a second calculation using the ideal gas law. So my first goal, I need to set up a stoichiometry dimensional analysis that will give me the moles of this H2 gas. So let's do that. So my first calculation here is going to be a stoichiometry calculation. And the goal here is to get the moles of H2 gas. And then after I get the moles of H2 gas, then my second calculation is going to be using PV equals nRT, and I'll take that number and I'll plug it in down there. Okay? So let's do my stoichiometry first. I need to do a stoichiometry problem to determine how many moles of hydrogen gas I have? Well, we know that stoichiometries require a mole-to-mole conversion, and so I know that I'm going to have a balanced chemical reaction so that I have these molar ratios. So let me write my balanced chemical reaction here first. So I have aluminum metal plus hydrochloric acid yields, and this looks like a single replacement reaction, single standalone element reacting with a compound. And so in a single standalone reaction, one element comes in and kicks out another element. So this aluminum is going to become a cation, which means it's going to kick out the hydrogen and not the chloride. So I'm going to get AlCl. Aluminum is a +3, chloride is a -1. So there's my formula for aluminum chloride plus H2 gas. Let's balance it. 1 aluminum, 1 aluminum, 1 hydrogen, 2 hydrogens, 1 aluminum, 1 aluminum, 2 hydrogens, 2 hydrogens, 2 chlorines, 3 chlorines. This is one of those least common multiple situations. So the least common multiple between 2 and 3 is 6. So I need 6 chlorines. So this becomes a 6, and this becomes a 2. So now I have 6 chlorines on both sides. Check again. 1 aluminum, 2 aluminums. I need to fix the aluminums. 2 aluminums, 2 aluminums, 6 hydrogens, and 6 hydrogens now. 2 aluminums, 2 aluminums, 6 hydrogens, 6 hydrogens, 6 chlorines, 6 chlorines, and it's balanced. There's my balanced chemical reaction. Okay, and that balanced chemical reaction is going to give me my molar ratios. So now I need to do the stoichiometry. So here's my balanced equation. Now I'm going to do my stoichiometry. And then I'm going to do my gas law. So my stoichiometry comes next. I'm starting with 30.0 grams of aluminum. And I need to convert it to moles of H2. So I'm going to convert grams of aluminum to moles of aluminum so that my grams of aluminum can cancel. Then my next step would be moles of aluminum to moles of H2. Moles of aluminum has to go on the bottom, moles of H2 on the top, so that my moles of aluminum can cancel. So my dimensional analysis is set up correctly. Let me put in my numbers. 1 mole of aluminum, this is a molar mass, 1 mole of aluminum is 26.982 grams per mole. And then my molar ratios here I get from my coefficients of the balanced chemical reaction. 2 moles of aluminum to 3 moles of H2. So now I'm going to do this math right here in my calculator to figure out the number of moles of H2. And of these numbers, these are exact numbers. There's 5 sig figs, 3 sig figs. So I need 3 sig figs. And my calculator gives me digits that will be rounded to 1.67. So I now have the number of moles of H2 that I've generated. So I've now done a stoichiometry starting from grams of aluminum, using the molar mass of aluminum to figure out the number of moles of aluminum, and then converting that to moles of hydrogen gas. So I've taken this high road right here so far to get to moles of hydrogen gas. And that's what's right here. Grams through the molar mass of aluminum convert to the moles of H2, so I have the moles of H2. So that's where I am. Now I need to find out the volume of this gas. I'm not going to use a molarity here because it's not a solution, it's a gas. So to do that, I'm going to take my answer from this problem, that determine the H2 moles, and I'm going to plug it into this equation, the ideal gas law, to solve for the volume of the gas. So let's do that down here. I'm going to first rearrange this equation to solve for the variable I'm looking for, which is volume. So for volume, to get alone by itself, I need to divide both sides by pressure. And so now it's volume equals nRT over P. So I'm going to start plugging in values. What is my N, number of moles of the gas? Well, I figured it out from my stoichiometry right up here. 1.67 moles of the H2 gas. That's the N value right there. R, 0.08206 liter atmospheres, or moles kelvins. And the temperature is given to me here. It's in Celsius, isn't it? So I need to add 273.15. So let's do that very quickly. 223.5 plus 273.15 equals 296.65. The Celsius temperature was only precise out to one place past the decimal. So with this addition, I can only go out to one place past the decimal. So that 5 is going to round that 6 up to 7. So this is going to be 296.7 kelvins. That's just a little bit of side math that I did to figure out what the temperature was. And then I'm going to plug in that temperature right here in my ideal gas law. 296.7 kelvins. Okay? All over the pressure. What is the pressure? They tell me up here it's 0.950 atmospheres. So look at that. We've done a lot of math, a lot of work to get down to this point, and all the rest of it is just plugging everything into our calculators. So let me do that. And the answer that I get has to be rounded to 3 sig figs, and it is 42.8. What units am I going to use? Well, it's volume, and I know that volume is going to be in liters. So there's my answer. 42.8 liters. So let's walk through this problem again because it had a lot of steps. Let's make sure that we followed along what was happening. It was asking for how many liters of a gas would be generated as a product of a reaction. So I knew that I was going to be solving at some point for the volume of gas. Now I wanted to make sure that I'm not using the volume of a solution. So I'm not going to be using a molarity here, a concentration of a solution. It's the volume of a gas. So I'm starting to think about the ideal gas law, which has volume of a gas. They give me the pressure and the temperature. So if I have the pressure and the temperature, and I know the number of moles of gas, then I can use the gas constant and solve for the volume. So if I've been given pressure and temperature, I know R, I'm solving for V, then I know that what I'm really looking for as the intermediate step is to find the number of moles of this gas. Well, that's what this scheme shows us. I need to find the number of moles of the gas. To do that, I'm going to do a stoichiometry to figure out the number of moles of gas that is generated. And once I have that answer, then I can do a separate calculation to plug it into the ideal gas law and get my final volume. Well, if you're doing stoichiometry, you have to have a balanced chemical reaction. So I had to write my equation with the correct formulas for the products and then balance it. Then I could do my stoichiometry. Stoichiometry is starting with grams of aluminum, converts to moles of aluminum, and then moles of H2 gas. And it gives me the number of moles of H2 gas. And that takes me to right here in my scheme. Once I have the moles of H2 gas, I'm going to stop my stoichiometry right there, and I'm going to do a separate calculation, plugging that number in for the moles of gas. And that's what I did over here. I used my gas law, my ideal gas law, rearranged it to solve for volume, and then started plugging in values. When I got to the temperature, I realized that I had to do a conversion to get it into kelvins, because all temperatures must be in kelvins for gases. And then I plugged all those values in, and then I have my answer. 42.8 liters. Okay, so that's how we approach this. There's a lot of moving pieces to it, so you've got to think strategically in terms of what you're trying to achieve at the end, how you're going to get there, what is the immediate step before you get your answer, how do you get the piece of information that you need to make that happen, and then kind of work backward. So with this in mind, you have the scheme here, you have a sample problem here. I'm giving you another sample problem right here, sample problem B. It's a very similar problem. How many liters of ammonia gas, NH3, would be generated from the reaction of 12.5 grams of hydrogen gas with 21.1 grams of nitrogen gas and they give us a temperature and a pressure. Now I'd like to point out two things about this problem that are more challenging than the one that I just gave you. So I'm giving you a problem that's a little bit more challenging than the one above. Have you spotted one of the challenges? Maybe you've noticed that now one of these reagents is not in excess. I've given you specific amounts of the two reagents and asked for how much product you generate. What kind of problem is this? If you said limiting reactant problem, you're right. So this is going to be a limiting reactant problem. So when it comes time to do the stoichiometry up here, I'm going to have to do two of these stoichiometries and then take the smaller of the two amounts. Remember, limiting reactant problems require us to do two separate limiting reactant calculations for the stoichiometry. So I'm going to help you set this up just a little bit. I need a balanced equation. Then I need the stoichiometries. So I need a limiting reactant calculation number 1 and a limiting reactant calculation number 2, right? And then you're going to do those calculations, take the smaller of the two amounts of the ammonia gas moles that are generated, and that value will then be plugged into your ideal gas law. To determine the number of liters of this ammonia gas. So that's one of the challenges that I've thrown in here, but I think by telling you about it beforehand, maybe it won't be too difficult, because you've done limiting reactant problems before. All right, have you spotted the other challenge? The other challenge you may have noticed is the chemical reaction here. You may not be familiar with this chemical reaction. This is not one of the predictable chemical reaction types. So I'm going to need to give you a little bit of help here on the equation. This is a combination reaction, and combination reactions, as you may recall, generally cannot be predicted. So I'm going to give you the equation here. Well, I'm going to give you the reagents and the product, but you're going to have to balance it. So hydrogen gas, H2 gas, is reacting with nitrogen gas. And in this case, there is only one product. It's a very important, industrially significant chemical reaction called the Haber process, by which we generate ammonia gas, a very important chemical. So there is the unbalanced chemical equation. So you are going to have to balance it first before you can use it for your molar ratios in your stoichiometries. Okay? So the same thing I did up here. You're going to balance the chemical reaction, run your stoichiometries. Since it's a limiting reactant problem, you'll have to run 2 of these. Take the smaller of the values, then use your ideal gas law, rearrange it to find what you're looking for. Plug in the moles, the smaller of the 2 molar amounts, and then solve for it. Make sure that everything is in the correct units and solve for it. So go ahead and pause the video, and while you're paused, you can work on that. And when you're done, you can come back and I will solve this problem for us. Okay, coming back from pausing the video, let's go ahead and get started on this. I'm going to first assign variables where I can up here in the equation, up here in the problem, so that maybe it will help me later as I start to plug values in. So it's saying how many liters of ammonia gas, that's a volume. Looks like I'm going to be looking for a volume. Would be generated from the reaction of that many grams of hydrogen gas. So in my equation, I've got 12.5 grams of hydrogen gas and 21.1 grams of nitrogen gas, so 21.1 grams of that gas. And I'm looking for, I don't know the volume of this in liters, is what I want. And I'm given a temperature right here, and I'm given a pressure, okay? And those will be useful when I get down here to my ideal gas law. All right, first of all, I know that I needed a chemical equation and I need it balanced. So let's balance this chemical equation first. 2 hydrogens, 3 hydrogens. So again, least common multiple math says I need 6 hydrogens on each side. So the way I get 6 over here is I put a 3 there. The way that I get 6 hydrogens over here is I put a 2 there. So now I have 6 hydrogens, 6 hydrogens, 2 nitrogens, and it's balanced. So now I have my balanced chemical equation. Now I can do my stoichiometries. What is the goal of my stoichiometries? It's to get the number of moles of this substance, so that once I get the moles of this substance, then I can bring that into the ideal gas law to solve for its volume of this gas. So my end point here of these stoichiometries is to get the moles of the NH3 gas. Moles of the NH3 gas. One limiting reactant calculation is going to start from the H2. The other is going to start from the N2. So I start with 12.5 grams of H2 gas. And the other starts with 21.1 grams of the N2 gas. So now, let's do the limiting reactant calculation. The first one in our stoichiometry, we're going to set up a dimensional analysis that converts from grams of hydrogen gas to moles of ammonia gas. So my first step is going to be grams of H2 to moles of H2. And then that cancels out my grams of H2. My next step will be moles of H2 to moles of NH3. Okay, so that the moles of H2 can cancel. So I know my dimensional analysis is set up correctly. I'm getting the correct units and substance at the end. And now I can plug in numbers. I'm going to use a little different color so it's a little bit easier to see. 1 mole of H2 is, on my calculator, it's 2 times 1.0079 equals 2.0158. 2.0158. Notice I've got 2 of them, 2 of those atoms in there, so I have to multiply hydrogen's atomic mass by 2. Now the molar ratios, 3 H2s for every 2 NH3. And there we go. So I have my numbers there. Let's go ahead and do the setup for the next stoichiometry. And so this will be grams of N2 to moles of N2. So I can cancel out grams of N2. And then the final step would be moles of N2 to moles of NH3. Okay? And with the numbers here, 1 mole of N2 is 2 times the atomic mass of nitrogen, which is 14.007, and that's 28.014 grams per 1 mole of N2. And the molar ratios, 1 mole of N2 to 2 moles of NH3. So now I have my 2 limiting reactant calculations set up. They're each going to give me some number of moles of ammonia. And as we know, in stoichiometries where you have limiting reactant problems, we're always going to take the smaller of the 2 amounts as the theoretical yield. So let me do some math in my calculator here. And the results of the top calculation gives me 4.13. And the results of the bottom calculation, if I round to the 3 sig figs, gives me 1.51. So of these 2 values, I always take the smaller of the 2. So there's the number that I'm going to use, 1.51 moles of ammonia. So this is the number of moles of NH3 that I'm going to generate. So if I look up here in my scheme, I have done the correct stoichiometries to determine the moles of my secondary substance, my product. So I'm right here now. Now I have to switch out and go to the ideal gas law to be able to determine the volume of my gas. And that's what I'm going to do here at the end. I have my ideal gas law. PV equals nRT. And I'm going to rearrange it to solve for what I'm asked for. I'm asked for the liters of the ammonia gas. That's the volume. So I'm going to rearrange this to solve for volume. Well, divide both sides by pressure, gets volume by itself. So volume equals nRT over P. So now I'm just going to plug in nRT over P. So the value for N, the number of moles, it's this one right here. That's what I got right there. And it's going to go right there. That's the number of moles of gas I have. 51 moles NH3 gas. R, I know the value for R. It's a constant, 0.08206 liter atmospheres or mole kelvins. And T is temperature in kelvins. Well, they've given it to me in Celsius, so I need to convert that to kelvins. So 1.50 in Celsius plus 273.15, and that gives me 274.65. And in this case, the Celsius temperature is given to me 2 places past the decimal, so I can keep both of those digits. So that's my temperature right there, 274.65 kelvins. All right, and then all of this is going to go over the pressure, which is 0.860 atmospheres. All right, so it looks like I have everything plugged in. The rest is just calculator math, so let me do that now. And based on the numbers that the calculator is giving me and the 3 sig figs that I will need to round it to, my answer is going to be 39.6, and these are in units of liters, right? Because it's volume liters, specifically of the NH3 gas generated, right? So there's my answer. Sometimes we have to use more than one approach. We will do a stoichiometry dimensional analysis to determine the moles of a gas generated, and then break it out into another calculation and use that in the ideal gas law. Use that answer in the ideal gas law to take it forward. You may also encounter another situation where you basically have to work backward from this. You may be given a pressure, a volume, and a temperature of a gas, and then asked for some number of grams of starting material that would be required. So you would have to work this problem backward. You'd use the ideal gas law first to figure out how many moles of product you're generating, then do stoichiometries to convert from moles of product to moles of the reagents, and then once you had the moles of the reagents, then you could convert from moles of the reagents to grams of the reagent. So you might have a problem that would require you to use the ideal gas law before you did the stoichiometries. But this is a classic example. We're very often interested in finding out what volume of gas would be generated by the addition of your reagents. All right.